Yeah, thanks for inviting me. It's always a great pleasure to be part of the Umbridge community. It's always really constructive and nice to be here and like to see what's going on in other people's worlds. If you can hear some screaming in the background, it's nothing bad. It's just my son who has just understood that he has hands and he's frustrated that he doesn't know how to use them. But I promise my partner is taking care of him. He's not alone. So I'm going to talk to you a little bit about kind of probabilistic modeling in general today. Um, so let's get started. I work for a company called digiLab, which is a tech startup in the UK. I'm currently working remotely. I'm actually in Norway right now, but our headquarters is in Exeter. And well, you can read kind of what our punchline is here, but we try to build kind of software, easy to use software for uncertainty quantification for the industry. And then we do a bunch of consulting as well. So this is kind of the motivation for my talk today. I think there's kind of an adaptation gap. We have all sorts of sophisticated methods for uncertainty quantification, but they're not quite widely used by the industry. So my question is why? I'm going to explore that a little bit today. There is one element of this, which is technical complexity, and that's something that Umbridge has set out to alleviate, and I think it has managed that, along with other software frameworks, of course, that makes it easier to, for example, define your probabilistic model, frameworks such as Pyro or Stan. But I think that's only kind of part of the story, this technical complexity. I think there is other barriers, which means that it's not used as broadly as it could be. I think that the industry isn't really properly aware of the relevance, and I think it's also sometimes very difficult to operationalize the models. And what does that mean? I'll get into that in a bit. So here's my agenda. I'll first talk a little about this relevance. Why is this not really seen as relevant to the industry? And then I'll talk about operationalization, which is connected with this idea of expert elicitation. How do you kind of define your probabilistic model or your uncertainty quantification model? And then I'll talk a little bit about some work that we've been doing recently in digiLab, just to get into some applications a little bit. So this first part is about this relevance question. Who really wants uncertainty quantification? So if you look at kind of like the topic just like superficially, it's really clear. Like uncertainty quantification is about making decisions under uncertainty. How can you use imperfect information to still find like actionable answers? And this could be important in safety critical deployments, especially, but also these other types of applications. And it's really about building trust and building trust in the models that you use, and being able to say exactly how wrong it is. So we've got lots of methods to do this. You have like these broad groups of methodologies for forward UQ, inverse UQ, and predictive UQ, and like you all know this. You work in the field. There's lots of methods, and you know, everyone keeps developing more and more. So we have all these methods, you know, ready to go, deploy, quantify the uncertainty, and we get, you know, these answers that we're looking for, or we don't. At least we're going to find out, you know, how much is the uncertainty? How much can I trust my model? So, you know, the industry should be lining up, you know, to use these methods, you know, and ask us to quantify all the uncertainty. I want to apologize for my use of memes here. I might have gone a little bit overboard in this presentation. Please let me know if this gets out of hand, and tune it down for the next time. But this is not the case, at least not in my experience from the industry. This is much more kind of the reaction that you get. You wave your flag, let's quantify the uncertainty, and at most you get kind of like a muted reaction here. And people go on with their lives. So why is that? And I think it's because uncertainty quantification isn't really interesting in itself. It's a means to an end, and it's an intermediate step towards going somewhere else. And in industry, especially, the people who kind of make the decisions are often the budget holders. So the people who are deciding how to use the money that goes for grant money, as well as for how to spend your money in a company. So the lingo that you use here is completely different. It's not about all these technical things. It's about much more often things that have to do with either money or regulations. And that's where I think that we can do a better job as a community in explaining what is really the value of uncertainty quantification. It allows you to much better estimate, for example, investment costs, as I've written here, provide robustness guarantees for predictions of forecasting models, and getting bounds on your risk assessments. And to the people who hold the budgets and who are deciding whether it's worth to invest the extra effort that it does cost to quantify the uncertainty, this is all about kind of reducing the investment risk. And I think it's important when we work in this field, if we want to actually make these offerings available to a broader audience, that we kind of start to think about that context. So that's the first bit of it. The relevance kind of barrier to uptake. So next, I want to talk a little about expert elicitation. How much is not a whole lot. So in my experience, when I deal with clients, maybe I'll start by asking them, when I try to figure out what's the prior on your data, or like where to begin with this probabilistic models, maybe I ask, how are the variables distributed? Because I look into my book of probability distributions, and I think, which one should we use? So I ask this question, and this is kind of the faces that the clients make. These are the questions. The replies that they give. What is a variable? That variable should probably definitely always be positive. Probably. This is the best case scenario. But often we kind of get sidetracked, and we promise to follow up later, and that often doesn't happen either. And I think this kind of like approach to expert elicitation, where you start with like this very technical way of considering the problem, is often unproductive and sometimes harmful. Because if you start by looking at this from this technical perspective, which probability distributions should I use, then you end up biasing the conversation, actually, and putting words into people's mouths, and you end up with a much kind of less realistic model than you could have had. So this is just kind of like my silly attempt to formalize this a little bit. Like, how do you actually begin to interrogate a client or a person who's not an expert in probabilistic modeling, and try to figure out how to operationalize their knowledge in a probabilistic model? So I think there's kind of two steps to this, and one of them is exploring. which means try to understand what is the domain that you're working in, understand the meaning of the different variables, and ask open-ended questions to these experts that you're trying to elicit their expertise from. And and it's really about communication. And this is a little bit of a, I think, paradox, because we work in a very technical field of uncertainty quantification, with everything is math, everything has an answer, and so on. But actually, solving real problems is a lot about communication. And then the second step is operationalizing, and that means actually putting this knowledge that you have elicited in the first step into something that you can compute, and that's choosing your distributions, and choosing actually which variables to even perform UQ on, but also yeah, yeah, that's it. First, try to be open, and then try to put the things into like something more formal. And that's kind of my experience with working with uncertainty quantification in the wild, if you will. So this is something I've been thinking about, and something that I'd like to dig further into, but I find it a little bit difficult to figure out where to start. There's another field of research where they've thought a lot about this, where they really considered how to use language to describe the things that they try to model, and that's cybernetics. So there's this really nice citation, I think, from Margaret Mead, where she describes cybernetics as a form of cross-disciplinary thought, which made it possible for members of many disciplines to communicate with each other easily in a language which all could understand. And that's the kind of hope that I have, that we can develop in probabilistic modeling, and which I think doesn't really exist at the moment. So how do we do that? How do we even construct a new semantics? How does one go about this in the first place? I don't know. What I would like is to, as I wrote here, allow domain experts to express themselves in relatable and precise terms, so that so that we can communicate about these things with much less effort, but still come away with a model that's precise and does the thing that we wanted to do. It has to be easy to use and easy to operationalize. So this is kind of an open question, and if you want to talk more about this, I'm very happy to discuss this. I think it's interesting, but I don't exactly know where to begin. So with that, I'll move a little bit on to some applications where I hope I can also illustrate where some of these things that I've been talking about are coming into play in kind of actual real life uncertainty quantification problems. So this is a project that we're doing with the UK Atomic Energy Authority, and it has to do with modeling plasma physics in a tokamak. So what you see in this picture is actually the plasma in a tokamak modeled by a gyrokinetic simulator. And so gyrokinetics is a sort of simplification of plasma physics. You take the Fokker-Planck equation and Maxwell's equations, and then the insight is that some of the movement is on a much faster time scale than some of the other movement. So these particles, they're kind of like racing through the tokamak in like a helix shape, but the rotational speed is much faster than the speed with which they go around the tokamak. So the gyro motion is this helix speed, and you average that out. So what you're basically modeling is a moving circle, which is the trajectory of the particle through the tokamak, and that reduces the problem from 7 dimensions to 6 dimensions. But as you can imagine, this is still extremely computationally demanding, and takes many hours on HPC machines. So what they want to do at the UKAA is to accelerate this a lot and emulate the response of the simulator. We have an Umbrage deployment, which is work in progress, and I think Chung will talk more about this tomorrow. But the kind of objective with this is to detect micro instabilities in the plasma. So there's two kinds. There's these microtearing modes and there's kinetic ballooning modes. And then to predict these quantity of interest, mainly the mode growth rate and the mode frequency. And these modes are these micro instabilities. And so we built this Gaussian process classifier for the microtearing modes, but also for the kinetic ballooning modes. And this is how the response surface looks like for the kinetic ballooning mode. So as you can see, it's like quite non-linear. But what I really want to tell you about is how like this model has developed, because they first set up some criteria for automatic labeling, whether this is a mode or it's not a mode. And then they gave us this data set and we started modeling it. And it turned out that it didn't work very well. And so we had to send them back, especially kind of like marking out some suspicious points, and they sent them back and said, yeah, actually they were mislabeled, and we sent them back again. And so it's been kind of like going ping pong back and forth, and that's what I call an iteratively manually updated, filtered by probabilistic anomaly detection. But it's really just us sitting and looking at the outcomes, sending it back to the UKAA. They update the labels and they send it back again. Because these automatic labeling criteria were just imperfect. So it's been a lot of back and forth, and it's very far from kind of the ideal model that you often see kind of in theoretical papers, especially. But going back and forth, we've arrived at a pretty good model. And yeah, you can see the confusion matrix there in the bottom right corner. And we're now at a point where this model is working well. With respect to the mode frequency predictions, there's some pretty funky stuff going on. So they wanted this modeled by a GP. They have some competition going on with a neural network group at the UKAA. And so they want to then see how GPs perform on this. And it turns out here that the standard GP model performs pretty poorly. And that's because there's some discontinuities in the data. You can see this plot here with the red and blue markers. The black dots is the true data, and so you can see that there's this jump happening at around 0.05 beta. So we tried something a little different, and we tried to use a mixture of experts GP. That's the red points on that same graph, where the standard GP is the blue points, and works much better, but it's still smooth, and it still kind of smooths out that transition. So I don't think GP modeling is exactly adequate for this model. We've tried to do gradient boosting just because it's kind of like the most dumbass way you can do regression, and it can do jumps like this. It shouldn't be a problem if at least there's kind of some system in the jumps, but it doesn't really work very well either. So we're kind of stuck figuring out where these discontinuities are happening. This is relatively high dimensional, and as far as I'm aware, I'm not an expert on the topic, but as far as I'm aware, like high dimensional change point detection is extremely difficult. But as you can see to the right, our mixture of experts model is still a lot better than the standard GP, and maybe good enough for their applications. So the last thing I'm going to talk about is another project that we've been doing recently. This is a collaboration with King Abdullah University in Saudi Arabia, and this is about a coral conservation program and reef restoration at an island called Shusha. And these nurseries where they grow corals, they're very sensitive to temperature and photosynthetically reactive radiation and some other environmental parameters. so they'd like to be able to kind of make a model of the temperature there. It's especially the temperature they're interested in, so that they can, on any given day, they can say, is the temperature out of range here? So it's a huge data set, or not huge, but in terms of GP modeling, it is huge. 250,000 data, which is more than is really tractable to do with an exact GP. So here we've used a stochastic variational Gaussian process. This is a well-established method for doing Gaussian process modeling for big data, where you use inducing points and you train them jointly with the other variational parameters, and you can do batch training. So you can take a chunk of the data one at a time, so you can actually kind of cycle through these 250,000 data points. We've done a bit of feature engineering, so nothing too fancy, but trigonometric time of year and time of day, and then transform the latitude and longitude to UTM coordinates, because it's a little bit nicer to pretend that the Earth is flat, at least locally, and this is a quite small area, so that's a good approximation. So our work so far has been kind of looking at what happens when we increase the number of inducing points to improve this GP approximation. And we're now using 16,000 inducing points, and we still haven't really reached a plateau for the loss function. And that's quite a lot of inducing points. We need to use top of the line GPU to even fit this into memory. And this is a deployment challenge. So there's something that we're considering right now, exactly how to deploy this, because they'd want to interrogate this model in real time. And it's just it's complicated and expensive to keep it running. So I don't know. Maybe Umbrit could also be used for deployment. We're looking into options. Yeah, and this is how kind of a prediction with this model looks like. We're building an app for them so they can go and explore this like in real time, as I mentioned. And yeah, that's now sitting with our software engineers. This is just a little bit of an advertisement. TwinLab is digiLab's platform. It's being remarketed under a new name. I don't know what it's going to be, but this is a surrogate modeling framework. And the other two are two open source packages that I maintain. TinyGA is an MCMC package, and Daft is a software package for sample thinning. You can find them on GitHub. Yeah. That's it from me. So yeah, I'm happy to take any questions.